Hello students. So we have seen two lectures. Now this will be a third lecture. Now here we are starting different laws of thermodynamics, and in that first law of thermodynamics that we are considering here, and in this case you must have studied that. So we'll see this first law of thermodynamics in zeroth law of thermodynamics. So here, if two systems are separated separately in thermal equilibrium, with third system they are in thermal equilibrium with each other. That means we have system A, right? System A will be, suppose system A is in equilibrium with system B, and we have system A is in equilibrium with the system C. Then you can say system A and system B both are in equilibrium. So that is what you can say zeroth law is saying. So here it is very simple, right? So here one example is given here, right? So here it is, first it is asked that system A and system B both are in equilibrium here, right? Then you can measure the temperature here for this. So T is provided for that, so we can measure temperature. And if you see system A and B are in same value, that means temperature of both the systems that is same, right? Then you can say A and B is in equilibrium, right? So now coming to next law, that is first law of thermodynamics, right? Here what it is said, that is energy neither be created nor be destroyed, but it can convert from one form to another form. It can transfer from one form to another form. That we have already seen this. So here we have seen one equation here that is very simple here, right? So that is, you can say, that is Q is equal to delta E. Delta E is nothing but, you can say, this delta E is nothing but delta U, that is change in internal energy, right? So that is plus W, work done. That means when heat is absorbed, right? So you will find there is a change in internal energy, and you will get some work done also by this system, right? And here Q is nothing but that is Q is you can say heat absorbed, right? Heat absorbed by the system, right? So this is what we have. So in differential form you can put this particular equation. This is dq and de or delta du, right? So here you can say de is equal to du, right? So that is in differential form, right? So this is very simple equation here what we have. Then as earlier I have said, energy can neither be created nor destroyed. This is, you must have studied this earlier, right? It can only be changed from one form to other. That's it. So this statement is made by, you can say, Rudolf Clausius in 1850. So this is the first law of thermodynamics. So this will tell about conservation of total energy. Remember, this law is very important because in chemical engineering you must have studied process calculation. In process calculation, energy balance equations we have written, right? So this is based on this only, right? So we should have, that means energy neither be created nor be destroyed. That should be there, right? So then only you can write energy balance with and without chemical reaction. So this is very important. So but it says about the direction of energy transfer, that only it will explain here, right? And conservation of total energy, so that is again explained by, you can say, first law of thermodynamics. And this particular law is very important in final year also, computational chemical engineering. So you are writing, or you are doing mathematical modeling, that means you are writing equations for any chemical engineering system. right? That equation is nothing but your energy equation. So what is the amount of energy in, suppose if I consider here, this is the reactor, so what is the amount of energy in it is coming here, and what is the amount of energy out, and at the same time what is this delta HR, heat of reaction. And for this, if you write energy balance, and this is unsteady state, suppose unsteady state, that means it is changing with respect to time, right? So inside this system, what change you are getting, that is also very important, right? And what is incoming from this, it is also very important, and what is outgoing from this is also very important, right? So this is nothing but your you can say input minus output, that is equal to accumulation. And at the same time we have to see what is the amount of energy generated in the system or absorbed by the system. So that is very important. So in that case, different terms that are considered here, you can say enthalpy term is considered, internal energy term is considered, then heat capacity is very important again, right? Then you can say enthalpy, that already heat absorbed, that is again very important, work done by the system, that is again very important, right? So this is very important here. So that part is explained by this, you can say, first law of thermodynamics here. So what is the statement of first law? Although energy assumes many form, the total quantity of energy is constant, and when energy disappeared in one form, it appears simultaneously in other form. So it is very important, when it disappears from one form, it will appear in second form. So that is the conservation of energy, you can say conservation of energy. And from that, you can say you will get energy equation. So this is very important here, energy equation what we are getting. So this will give energy balance. So this is from, and this energy balance can be written at steady state, that means nothing is changing with respect to time, and unsteady state, that means it will change with respect to time. So this part, right? So that's why this first law of thermodynamics is very important, right? So applications where you can say, right, you can say if you have a process, right, process is divided into two parts. One is, you can say, system, and second is surrounding, right? And process, that means something is getting changed in the system, so that's why it is process. So here, suppose if I consider a simple reactor here or simple container, right? So something is incoming here, something is outgoing here, right? And this part is system, this is rigid boundary what you will get, this is your system here, right? And what change you are getting in the system, that is maybe change in temperature, maybe change in pressure, maybe change in concentration, right? So this you can say process variables, right? Already we have studied this in earlier lecture. And because of this change in this particular parameter, that system is called as, you can say, this is called as process, right? And in vicinity with, you will get here surroundings, right? Surroundings. And this, you can say, this is system here, right? So this is your system. So this is separated by, you can say, rigid boundary, right? So system may be of any size, right? That depending on the application, right? So this is very important. If you are writing energy balance for earth, so your earth will be your you can say system, right? And around this earth, whatever it is present, that you can consider as a surrounding. So it will be, have any size. You just write down the balance equation, energy balance equation here, but this is very complicated case here, right? So what separates your system and surrounding, so that is, you can say, a boundary. So boundary what you have, so which separates your system and surrounding, this boundary may be real, right? Real, that means visible, it is present there, or you can say sometimes it is imaginary, right? So you can just have a line sketch, that means you can say this is what we have, right? So this is, you can say, system here, and here you have surrounding, right? right? Here we have surroundings. So this you can say imaginary. That means you have drawn this line in somewhere in universe, right? So this is imaginary boundary. Sometimes it is rigid or flexible. So rigid means you can say we have a reactor, right? And this is thick wall reactor. That means material we use for this is thick wall, right? And that's why this is rigid. That means it is not moving, right? And second, you can say flexible. That means if you take a balloon and if you blow the air inside this balloon, you will find this balloon is getting changed, or the size is getting changed. So that type of boundary is flexible here, right? So this is very important. So here first law of thermodynamics focuses attention on particular process here, right, of interest, right, on the equipment, that means different reactors, different separating equipment, or you can say material directly involved in the process, right? So this is very important here. So only that part it is considered during this particular study, right? So we are not considering any extra whatever it is there, so that is not considered, right? That is not required. So what is focus? If I consider a reactor, surrounding of that reactor is very important. That only is sufficient. And what is happening in the reactor, so that is only can be considered here, right? So that is, you can say, all about, you can say, first law of thermodynamics, right? Now if you see this how this first law is applied to system and surrounding, right? In this case, if you see system and surrounding, not to the system alone, right? Remember, so this is this first law is applicable for both these things. That means if you have this system here, right, this is system, and this is, you can say, surroundings, right? That means whatever you are getting change here, right? Why this change is getting here? Suppose heat is absorbed from this side to this side, or heat transfer is there from this side to that. That means surrounding is losing energy, right? And system is gaining energy. So that means there is a change. What change is there? There is a delta change in surrounding. That means it is lost by the surrounding, right? And at the same time there is a delta change in system that is gained by the system, right? So one is lost and another is gained, and if you add this together and total amount of this energy remains same, so that's why this change is always equal to zero. That means if you add this change of energy in the system and change in energy of this surrounding, so if you add this together, that will be equal to zero, right? So change in system, that may be change in internal energy, right? Its internal energy might be getting changed, or maybe it's potential energy, or you can say it's kinetic energy. These are the three forms which are very important, right? So one is internal energy, second is kinetic energy, and third one is, you can say, potential energy. So these three cases are very important, and anyway these are measured in this form only, right? So change is measured here always, right? So in the context of thermodynamics, you can say heat and work represents energy in transit across the boundary, right? So this is very important. So what is getting changed? Why this kinetic energy or potential energy, or you can say internal energy is getting changed? Because heat is added, or work is done by the system, or work is added to the system. So this is because of that. That means here you can say, suppose you have a system here, right? And if you put some agitator here and some liquid is present here and start rotating this here, right? And as soon as you start rotating, some work is done on the system, and this is rigid boundary, suppose, and it is insulated here, right? It is insulated here. So in this case, what will happen? Some work is added here. Because of that work, work is stored as an internal energy in this system here, right? It will store as internal energy, and then it will release as a heat here, right? So its temperature will increase here, temperature will increase. So what is change you are getting here? So here you are getting change as internal energy. Because of increasing temperature, might be kinetic energy of molecule may change here, right? So this is possible here. So this is what we are getting changed, and because of change in some molecule place here, maybe we have to see for potential energy, no doubt. But so these changes we are getting because of addition of work, or you can say addition of some heat, or you can say extraction of some heat, that we have to see, right? So these, that means work, that is W, and you can say heat, both are in transit. That means they are transferable. That means you are adding that. Okay, that is crossing the boundary here, right? And they cross the boundary, right? That dividing the system and surrounding, and are never stored and contained in the system, right? So that means they are always in stored in internal energy. It may store in internal energy, or there might be change in kinetic energy or potential energy. So that is what we have. So here potential, kinetic and internal energy resides with and are stored with matter. So that's what I am discussing earlier, right? So Q is always in transit, work, that is always in transit, right? But these are in stored form. Okay, heat and work represents energy flows to or from a system. That means to the system heat can be added and system can do the work, or system does the work, or you can say on the system work is done, heat is transferred to the surrounding. So this is possible, right? And because of this you will get a change in potential, or you can say next is kinetic energy or internal energy, right? So that represents the quantities of energy associated with the system. So if you write the energy balance equation for closed system, because you have studied this very well in process calculation, right? So here energy balance. So as first law tells, energy cannot be created nor be destroyed. It can be transferred from one form to another form. So we'll apply this. So how we can apply this when we are saying closed system? So this is, you can say, closed system. Here no matter is getting transferred from system to surrounding, right? System to surrounding, it will not get transfer, only energy can transfer, right? So that's why this is here. So here boundary does not permit to transfer the matter between the system and surrounding, right? So this is said to be closed closed system. This is considered as closed system, and mass is necessarily constant here, right? So that is what we have. Because no stream enters or leaves the closed system, that means nothing is leaving the system, nothing is entering the system, no energy associated with matter is transported across the boundary that divides the system and surrounding. What divides the system and surrounding? Boundary. Boundary divides the system and surrounding. And here that means, remember, if you consider some matter means some material here, and if it is entering the system, and every matter is maintained at some temperature, that means it has some energy there, right? And when that matter is entering system, that means some energy is added to that system. That is very important, remember. And here no matter is entering, no matter is leaving, right? So therefore mass of that particular system is constant. So there is no addition of energy or loss of energy because of you can say mass flow, because no matter is exchanging, so mass flow is equal to 0 here, right? So in this case here, therefore energy exchange between the closed system and surrounding, right, it is in the form of only heat and work, right? Are you getting this? Then total energy change of surrounding is equal to net heat transferred to or from it as heat and work. That means if you calculate change in energy in surrounding, what is that? If Q is lost, right, Q is given here, system will do some work, right? So Q is added here, this is okay. So Q minus W. So that's why plus minus sign it is added here. In second case, if work done is here, right, or it is mentioned here. If it is reverse case, and then this might leave some energy, it will give some energy to surrounding, right? So this is possible. So this equation is holds good, where Q, heat Q, and work always refers to the system, remember. So we adopt the convention that makes the numerical value of both quantities positive for transfer into system from the surrounding, and if there is a transfer from system to surrounding, that will be considered as negative, right? So here it is lost, the work is, or here Q is lost, so it can be considered minus here, right? If Q is added, so it is plus here. Work done by the system, so it is minus here, right? Work added to the system, so it will be plus here, right? So this is very important in this case, so that will be your sign convention here. So energy balance, again, if you continue, so here we have some this we can say Q surrounding and W surrounding, right? So these are, you can say, work and you can say heat and work of that surrounding, right? So here then Q surrounding is equal to minus Q, right? And W surrounding is minus W, right? Why it is written like that? Because when you are writing for surrounding, this is the Q lost by system, so that's why it is minus, and it is gained by the surrounding, that's why it is plus for surrounding. And here work done by the system on surrounding, that's why for surrounding it is plus, and work done by the system, that means it is lost from, something is lost from the system, so that's why minus sign here. So therefore delta change in surrounding is, you can say, Q surrounding plus W surrounding, right? So this is equal to minus Q minus W. So this is for, you can say, this is written for system, right? So but it is equivalent to, you can say, for surrounding, right? So only sign change you will get here. And if you write for system, right, so it will be Q plus W, Q plus W. That means if you heat and work is added, that means for that particular system Q is added and work is also added, so both are positive here, right? So this is the case. So this equation states that total energy change of closed system equal to the net energy transfer into it as heat and work. So total energy change, if you see for system, so that is the amount of work added to the system or done by the system, or heat added to the system or done by the system, or lost from the system. So that is very important. So for closed system, often these closed systems often undergoes the processes during which only internal energy of that system getting changed, right? So closed system, nothing is moving, so your kinetic energy is 0, potential energy is 0 here, right? So only, you can say, you will get internal energy, right? So that value, we have some x value, suppose, and therefore you will get that change in system what we have. So this equation here, this equation, if you see here, so this is added here, so this is converted as, so delta change in system is considered as delta U. T, superscript T, is for total here, equal to Q plus W, Q plus W, okay, where UT is the total internal energy of the system. So it is mentioned there. So again, in continuation, in differential form, if you write, so delta is replaced by differential element, right? So delta is for finite difference, right? It is a direct change, what you can say, from one point, this point, and another point, and this change, what is the change? So this is 2, this is 1, suppose, so you can say x2 minus x1, this is, you can say, delta x. But here you have in differential form, so differential form, you are putting that there is a continuous change you are getting here, so that's why this delta is replaced by d, that is differential change, and here this is finite difference here you will get. So symbol Q, W, U, this is for entire system, right? And that system may be of any size, remember, it is, right, any size, but initially you have to define this system clearly, right? It should be defined. That means we have to define the boundary, right, that separates your system and you can say surrounding, right? So VT, V superscript T, that is a total volume, and total internal energy is UT. That depends on the quantity of material in the system. That's why these are extensive properties, no doubt. Already we have discussed this earlier. So therefore this Vt is m into V. M is mass here, right? Right? And then V is specific volume here, that is volume per unit mass. This volume per unit mass. Vt again can be defined as N into V. N is number of moles here, and then this V can say it is a molar volume. So V is nothing but your meter cube per moles, right? Are you getting this for second case? So similarly here, UT is the total energy and M is the mass here, and this is internal energy per unit mass, and here N is number of moles, and here U is internal energy per unit moles. So here plain symbol you can say U or V, that represents volume and internal energy per unit amount of material, either unit mass or unit mole. So that depends. So that means when to use N and when to use M, that is again very important. So these are specific and molar properties, right? So specific and molar properties. What is specific? You can say when you are considering with respect to mass, that is specific. That means specific volume, and this is molar volume, right? So that is the difference here. So specific internal energy, or you can say molar internal energy per unit, or energy per unit moles, right? And these are intensive. Why? Because it is per unit mass or per unit number of moles. So that's why you can say it is that quantities are independent of matter present in the system. That's why you can say these are internal. These are intensive properties. Then energy balance for closed system. Again, if you continue like this, here if you see, this is total volume and this is total internal energy for homogeneous system. Homogeneous system, already we have discussed earlier, of any size are extensive properties, and specific or molar volume or specific or molar internal energy are the intensive properties. As I think in previous slide we have discussed this. Therefore, for closed system of n moles, you can have equation delta Nu is equal to n is constant here, you can take out. So n into delta U is equal to Q plus W, and in differential form you can put this n into du, that is equal to dq plus du, right? And if you consider n is equal to 1 here, so then it will be disappear. So delta U is equal to Q plus W. Remember this equation, many times we are using this, right? So this equation is necessary, and du is equal to dq plus dw. This is in differential form. This is in differential form, and this is in difference, that is finite difference you are applying here, right? So it is equivalent to that, right? So closed system, reversible process, enthalpy. In differential form, here if I put n is equal to 1, so this equation is possible here. So here you will get dH is equal to du plus differential PV, right? And on integration, so this is in difference formula, right? So it is very simple. So now coming to a second aspect of this particular topic, that is reversible process. A process is reversible when its direction can be reversed at any point by infinitesimal change in the external condition, right? So this is the definition. It is very simple here. The reversible process is ideal in that it produces a best possible result, right? And it yields minimum work input required for maximum work output, right, attainable from a specified process, and it represents a limit to performance of any actual process that is never fully realized, right. So this is the upper limit, you can say this is upper limit, right, for actual process. So here we are considering when the process is reversible, so this will produce maximum possible work here, right. And then when we are considering actual system, so actual system will produce work always less than this you can say reversible process. So what is this reversible process? If you see this particular diagram here, so this is you can say piston cylinder arrangement, and some assumptions here we have made, that is so this is the weight here added, this is the weight, right, right, weight what we are adding here. So then then here you can say this is in equilibrium initially, right. So then piston here it is considered as a frictionless, right. And if I remove this weight from here, this is weight mass, it is added 1 2 3 4 5, and here if I remove one from this, what will happen? It is imbalanced now, right. And then inside pressure will apply on this piston and it will move up, right. And it will move up, but it will go up to certain limit, and then because of this weight already it is present here, it will move down again, it will move down, so up down, so oscillations will start, right. And finally it will balance at particular value, right. So then you will get here this change in you can say uh, displacement here, this delta L, this is displacement into area of cross sectional, here you will get this is delta V, right. So change in length, so this is very simple already, this is length and this area, so change in volume you will get here in this reversible process. You can take out P, so that is also possible here. Now one more definition here, you can say heat capacity. Many times this is another important aspect in thermodynamics, right. Many times you must have studied Cp, Cv, right, those are required, right. So here you can say constant volume heat capacity, it is of substance is defined as Cv, right, as a differential change in internal energy with respect to temperature at constant volume. And constant pressure heat capacity of substance is defined as Cp is equal to differential change in enthalpy with respect to temperature at constant pressure, right. So if you see this at constant volume process for closed system, again remember, so du is equal to Cv dt at constant volume. Why this is? Because we have seen for constant volume process, we have from first law of thermodynamics, we have du is equal to q plus w, right. So in this case, for constant volume process, your w will be equal to 0, right. So that's why you will get du is equal to dq, you can say here, sorry, dq, right. So dq is what? So here I will define dq is equal to Cv dt, right. ये कहाँ से आया? What is this dq is equal to Cv dt? This is nothing but from this equation is analogous to this here. If you see this is very simple, right. Okay, so in this case we know that change in internal energy delta U. So if you write this in different form, that is delta U is equal to Q plus W. This is again first law of thermodynamics. Here W is equal to 0, that means Q is equal to delta U, right. This is applicable for first law, sorry, this is for constant volume process. So this here this can be integrated then, so it is very simple because Q is replaced by Cv dt here, and then you can get delta U is equal to integral Cv dt and integral limit T1 to T2. So for mechanically reversible constant volume process, you can write Q is equal to delta U, right, as discussed here, If W is equal to 0, so you can say Q is equal to delta U, right? So it is mentioned here, and that particular simple equation you will get for heat capacity. So similarly, if I say, yeah, this is for n number of moles, right? So this is again very simple. So only n is added here, no doubt. For constant pressure closed system process, right? So dH is equal to CPdt. We have seen this earlier in previous. So here you can say already we have discussed Cp is equal to del H by del T at constant pressure. So constant pressure, so it is Cp is equal to dH by dt at constant pressure. So dH is equal to Cp dt. This is already discussed here. So this, from this you will get this particular equation here, right? And if you integrate this, you will get delta H is equal to integral Cp dt with limit T1 to T2. And at constant pressure process, again you will get this simple equation here, right? Q is equal to delta H integral T1 to T2, right? So how you got this? This is from, again you can say delta U is equal to Q plus W, and W is equal to minus PdV. So it is delta U is equal to Q minus P delta V, right? This if you add here, so here Q is equal to delta H you will get, because internal energy plus PdV, that is delta H. So this is added here. This is very simple. So another form, if you see for n number of moles, n is added here. So this simple equation is possible at the end. Okay. So this is you can say for heat capacity, right? So thank you here for this particular lecture. We have completed first law of thermodynamics, right? And some definitions, that is heat capacity, and we have seen the mechanical reversible process, right? So that part is completed here. So thank you. So we'll see PVT behavior in next lecture, pressure, volume, temperature behavior, and from that we have to see the different equation of state. So that is again very important. So that we'll see in next lecture. You can subscribe YouTube channel, which is already shared on your WhatsApp group, right? And you can see these lectures there. Thank you.